Suppose we have a circle and a point outside of the circle, and suppose this is a line that intersects the circle in 2 points, and this is another line that intersects the circle at 2 points. Both lines pass through this point here. And I've marked this distance is x1, this distance is y1, this distance is x2, and this distance is y2. And the question here is, what can we say about x1, x2, y1, and y2? Is there a relationship between them? And the answer is, of course, yes, there is. Consider this triangle and this triangle. They are similar. Why? Well, because if this angle is alpha, then this angle is 180 minus alpha because this is a cyclic quadrilateral. And now, since this is 180 minus alpha, the complementary angle here should be alpha. So this triangle and this triangle share this angle and have the same angle here and here alpha. Now we can use the properties of the similar triangles, namely that they have proportional sides. So this time, x1 divided by the corresponding side in the other triangle, the one that lies against the green angle, which is y2. So x1 divided by y2 equals, and then the other two corresponding sides, x2, the one against angle alpha, divided by y1, the one against angle alpha again. And that's how we get this equality. Now we can multiply both sides by y1, y2, and then we get x1 times y1 equals x2 times y2. And let's see how this looks on the picture. x1 times y1 equals x2 times y2. And there were no restrictions on the choice of these two lines as long as they passed through this point and intersected the circle at 2 points. So if we got a different line here, it would also satisfy that, for example, x3 times y3 equals this x1 times y1 equals x2 times y2. And so this value equals this value equals this value, and this value doesn't depend on the line we chose. And so this value is somewhat intrinsic of the circle and the point. So this quantity is called the power of the point A with respect to the circle K, and is written like this: pow of A, comma K. And this property also works in the opposite direction. Suppose I take the point A and I draw two random lines and I choose 2 points on each line such that this times this equals this times this. It will follow that these 4 points lie on a circle, or that this quadrilateral is cyclic. So we have that x1 times y1 equals x2 times y2, where x1 is this, y1 is this, x2 is this, and y2 is this. And let's prove now that this quadrilateral is cyclic. Again, consider this triangle and this triangle. Well, they are similar because they share an angle, and the ratio of the sides at that angle in both triangles is the same, because this can be rewritten as x1 divided by x2, which is the ratio of the sides of this triangle, and it equals y2 divided by y1, which is the ratio of the sides of this triangle, the sides at this angle here. And therefore, the angle that lies against the side x2 will be equal to the angle that lies against the corresponding side y1. And if we call this angle alpha, then this angle here, as a complementary to this one, would be 180 minus alpha. And so the sum of the two opposite angles in this quadrilateral is 180 degrees, which means that it's cyclic. Here's the optional problem. We have a triangle and an incircle, and this is the incenter of the triangle. And we draw this line through this vertex and the incenter. It intersects the circle at these two red points here and here. Then we drop a perpendicular from this point to this line here, and we connect these 2 points. And then we drop perpendicular from the incenter to this line here. And that's how we get the other 2 red points, this point and this point. The objective is to prove that the 4 red points lie on the same circle, that this is a cyclic quadrilateral. And here's the solution. First of all, this line connects the vertex of the triangle with the incenter, and so it's an angle bisector of this angle, so this angle equals this angle. And now we notice that this here is a perpendicular from a vertex of the triangle to an angle bisector of some other vertex, and therefore it must lie on the line defined by 2 of the tangent points of the incircle. In this case, this is this line. Furthermore, we know that this is perpendicular to this, and this is perpendicular to this, because this is the center and these two are points of tangency of the circle and these sides. And therefore, here we have a cyclic pentagon. We have that this angle equals this angle equals this angle equals 90 degrees. And so these 5 points lie on a circle with diameter this segment. Now let's consider the powers of this point with respect to this circle and this circle. Well, with respect to this circle, the power of this point is this times this, and it equals this times this. And with respect to this circle here, the power is this times this, and it equals this times this. But now observe that this times this is common for both the power of this point with respect to this circle and the power of this point with respect to this circle. And so the two powers are equal, and they're equal to this times this. And therefore, this times this, which is the power with respect to this circle, equals this times this, which is the power with respect to this circle. And because this times this equals this times this, we have that this quadrilateral must be cyclic.